Welcome back everyone. In today's video we are going to solve this problem, which is from EGMO 2024, which was held in Georgia, in my country, and it's problem 3 out of 6 problems, and the statement is pretty easy. So we call n singular, just call this good. We call n good if for any divisor of n we know that d times d plus 1 divides n times n plus 1, and we have to prove that for every 4 distinct integers which are good, their greatest common divisor is 1. Okay, so we know that d times d plus 1 divides n times n plus 1, and actually it's really nice problem. I mean, there are lots of problems which are worse than this, but this was actually suitable for problem 3 for EGMO, and not so boring, and just anyways. First, you can try cases like n equal to 1. Now this implies that d could be only 1, and we know that 1 plus 1 is 2, so 2 divides 2. Okay, and now consider n equal to any prime. Now this implies that d is equal to 1, or d is equal to p itself. If d is equal to 1, then this implies that 2 divides p times p plus 1, which is true for every positive integer, not just for primes. And if d is equal to p, then this just implies that p times p plus 1 divides p times p plus 1, and this is of course true. So we see that n is good if n is prime number, so every prime number is good. And now we will prove that number of divisors of n is less than or equal to 2. So this means that n is equal to some prime number, or n is equal to, actually let's call this Gn, and wait, okay, so let Gn be equal to number of divisors of number of different divisors of n. So for example, if n is equal to 12, we know that number of divisors of 12 is 3 times 2, which is equal to 6, but in our case we get that G12 is equal to what? Is equal to 2, because only 2 and 3 divides this number. And yeah, okay, let Jn be equal to this, and we will prove that Jn is less than or equal to n 2 for every good number. So let n equal to okay, I will speed this process because this takes time. So let's say that n is equal to this right here, and these primes are such that p1 is uh, less than p2, which is less than p3, and so on, and this is less than pk. Okay. uh, okay, so we know that p1 is the smallest um, divisor of n. So let e equal to p1. This implies that p1 times p1 plus 1 divides n times n plus 1. Okay, and we also know that um, actually let d equal to um, this number. Okay, so this is the biggest divisor of n, other than n, of course, and this implies that fraction of n p1 times this divides n times n plus 1. Okay, now um, um, okay, so now we can just, so this second statement implies that okay, so we have this from the second statement. So this n goes away. Okay, so we have this left, and now okay, so this is same as just n plus p1. Okay, and we can just disappear this, and we can move p1 to the right side. So this implies that n plus p1 divides p1 squared times n plus 1. Okay. Now we can replace n with this, um, with this. So we have not okay, it's visible. Okay, and we have this divisibility. Now we can just remove p1 from the both sides, so we get um, this whole thing, but the difference is that we put this here and plus 1 here, and we can remove this like this. Okay, so now we have this, and let's call this, so let's this equal to m. Okay, so this is m. Now this implies that m plus 1 divides p1 times m times p1 plus 1. Okay. Okay, so we have this because this is m and this side is m plus 1, and n is just p1 times m, so we get m plus 1 divides p1 times mp1 plus 1. Now we can move, this is same as m times p1 square, p1 square plus p1. Okay, and now if a1 is more than 1, so 2, 3 or bigger than that, but actually we don't need this. Okay, so if a1 is equal more than 1, we know that p1 divides m, because we know that m is equal to this, and power of p1 is a1 minus 1, which is more than 0, which means that p1 divides m. And since we have that m plus 1 divides p1 squared plus p1, we know that p1 does not divide m plus 1 because it divides m. This implies that p1 and m, GCD of this, is equal to 1. So we can just remove p1 from the right side, and we get m plus 1 divides m p1, actually mp1 plus 1. And now if a divides b, we know that a divides b minus 1, so this simply implies that m plus 1 divides m times p1 plus 1 minus m minus 1, which is just equal to m times p1 minus 1. Okay, and we know that GCD of m and m plus 1 is equal to 1, so this implies that m plus 1 divides p1 plus minus 1. Okay, and now this also implies that p1 minus 1 is more than or equal to n plus 1. Now we know that p1 minus 1 is less than or equal to p1, actually less than p1, and n plus 1 is more than m, which is equal to p to the power of, actually I will copy this. Okay, so we have this inequality, and since p1 is the smallest prime divisor of m, we know that every p, so for example p2, p3, or other prime divisors are bigger than p1, so we know that m is more than p1 to the power of sum of all the powers, so a1 plus a2 plus a3, a1 plus a2 plus a3 plus so on, and minus 1. Okay, and since p1 is more than this, we know that 1 is more than a1 plus a2 plus so on minus 1. So we can just move this to the left side, and we get that actually left side 2 is less than of this, and there's only one option, that this is equal to 1. And we know that a1 we know that a1 is more than 0, so a1 must be at least 1, and this implies that a1 is equal to 1. Okay, and this implies that m is equal to p1. Wait, yeah, m is equal to p1. Now if a1 is, wait, where was the assumption? Wait, actually we had that a1 was more than 1 right here, so this is actually contradiction, so this just and this implies, this was actually contradiction, that's my bad, contradiction. And instead of if, right, so we know that a1 is equal to 1. We can't say that a1 is equal to 0, because if a1 is equal to 0, then p2 is the smallest divisor, and we have to do the same thing for the p2, and that's just infinite descent or something like that. So we know that a1 is at least 1. Okay, now if a1 is 1, then we have actually process is almost the same, so we are yeah, so in this case, okay, so we have this, and since a1 minus 1 is 0, we can just remove this. Okay, and now we are left with this kind of usability, whatever. And now we will call this the m. So let's call this m. Let m be equal to this. Okay, so we have m plus 1 divides, let's just call p1p because it's easier to write, p times pm plus 1. Okay, and in this case we don't know that p and m plus 1 are coprime, so we have to do something without this. So we have m plus 1 divides p squared times m plus p, and this implies that m plus 1 divides p squared times m plus 1 minus p squared times m plus p. Like this. And this is simply equal to p squared minus p. So we have p m plus 1 divides p squared minus p. And this also implies that p squared minus p is greater or equal to m plus 1. Now we know that okay, so this is more than m, and p squared minus p is less than p squared. Okay, so we have inequality that p squared is more than m. Okay, and we know that m was equal to this. Okay, and this is greater than p to the power of sum of all powers, so a2 plus a3 plus a4 and so on, plus all the way to the ak. Okay, so we have that a2 no, actually 2 is greater than a2 plus a3 plus a4 and so on, plus ak. And we know that this is equal to, this is greater than 0, so this should be equal to 1, which means that there exists only one integer e such that a e is equal to 1, and this implies that n is equal to p1 times pi. So let's just write that n is equal to pq. Okay, and that's what we wanted. Actually, we wanted that number of different prime divisors of n was less than or equal to 0, 2. Now we will prove that if n is good and n is equal to pq, then mm, q is equal to p squared minus p plus 1. So that's our second claim. So we know that p times p plus 1, actually let's assume that p is greater than q. Okay, we know that p times p plus 1, actually p is greater than q, but p is not equal to q plus 1 for every p, so we can just write this because p is not equal to q plus 1. So this divides in pq times pq plus 1, and we also have that q times q plus 1 divides pq times pq plus 1. Now we will use this right here. So if p is greater than q plus 1, then q plus 1 can't divide p. So if it divides, then q plus 1 should be equal to 1 or p, and both of these are contradiction. So this just implies that q times q plus 1 divides q times pq plus 1. Okay, and we can just remove q's from the both sides, so we get q plus 1 divides pq plus 1. Okay, now this means that actually we can subtract q plus 1, so minus q minus 1, which is equal to q times p minus 1. And since q and q plus 1 are coprime integers, this implies that q plus 1 divides p minus 1. And this implies that p is equal to some number k times q plus 1 plus 1. Okay, so we have p is equal to k times q plus 1 plus 1. Now this was the second divisibility. Now we will use this somehow. So we can simply remove p from the both sides. So p plus 1 divides q times pq plus 1. Okay, now if q if GCD of q and pq q and p plus 1 is equal to 1, this implies that p plus 1 divides pq plus 1, and this implies that p plus 1 divides p times q minus 1. Okay, and since p and p plus 1 are coprime numbers, this once again implies that p plus 1 divides q minus 1. And what this means is that q minus 1 is greater than or equal to p plus 1. But we know that p is more than q plus 1, so this is more than q plus 1 plus 1, which is q plus 2, and we get that q minus 1 is greater than q plus 2, which is contradiction. actually. Okay. So we get that um, q divides p plus 1. Okay. So if now this implies that p is equal to um, qt minus 1. Qt. That's actually name of this problem, but okay. So p is equal to, wait, actually now let's replace p with this. So we know that p is equal to this. Okay. Um, so q divides k times q plus 1 plus 2, and this is also same as q divides k plus 2. Okay, so let k be equal to I don't know, qt minus 2, I guess. Okay, so we know that k is equal to qt minus 2. Now actually let's put k into t into k and k into p, and we get p is equal to k times q plus 1 plus 1, which is equal to qt minus 2 times q plus 1 plus 1, which is equal to q square, actually t times q square plus tq minus 2q minus 2 plus 1 minus 1. Okay, well, this is not cute, but you know, we can work this out. So p plus 1, we need p plus 1 actually. P plus 1 is equal to this. Okay, so this is same as q times qt plus t minus 2 divides q times, oh no, we have to put qp into this. Oh, that's unfortunate. So if this is p, then this is q times this. Actually, do we need this? Actually, well, kinda. So we have q cubed plus q squared t, q squared t minus 2q squared minus q and plus 1. Okay, finally. So we have this. well, not okay. We can remove q's from the both sides, so we get this. Okay, and now what we have to see is that okay, so we have to notice that this equation is actually wait, are we missing t here? Yeah, we are missing, so we need t here because it's q squared times t multiplied on q, which is q squared times t, so t times this. Okay, so okay, like this. And now what we have to see is that yeah, this is equal to q squared times qt plus t minus 2 plus minus q minus q plus 1. Okay, so this equation is equal to this, and if we subtract q squared times qt plus t minus 2, if we subtract that equation, actually if we subtract this equation to the equation which I said earlier, which was that q squared times qt plus t minus 2, so this times q squared, we will get that qt plus t minus 2 divides t minus 1. Okay, we have this equation, and now this implies that q minus 1 is greater than or equal to qt plus t minus 2, which is same as this. So we have q is greater than or equal to qt plus t minus 1. We know that t is not equal to 0, so t is at least 1. Now if t is more than 1, then we know that this is more than qt, okay, because t minus 1 is greater than 0, so this is more than qt, which is more than q, because t is at least 2, and this is contradiction, which implies that qt plus t minus 2, this implies that t should be equal to 1. Okay, t is equal to 1. Now this implies that, so if t is 1, we have k equal to qt minus 2, which is just q is equal to q minus 1, 2, and p is equal to this. Actually we don't need k, we need only p, so p is equal to q squared plus wait, this is, yeah, plus q minus q, which is minus q, and this is equal to p plus 1, so p is equal to minus 1. and we get the same exact of thing what we wanted, actually like this. Love it. So we know that if P and Q PQ is a good number such that P and Q are prime numbers, then greater prime, so in our case P, is equal to Q square minus Q minus 1. And with that we are almost done, because so we wanted to prove that GCD of A, B, C and D was equal to 1. Now if A is equal to PQ, some number PQ, then there should be B, so P should be equal to P times some prime R, such that R is not equal to P, okay? And this implies that C should be equal to Q to maintain the GCD Q. So yeah, so at this point we have greatest common divisor Q in A, B and C. The reason why C is not Q times C for some prime C is that if Q is equal to QC, like this, okay, so if there exists some S such that C is equal to QS, this means that S, so if A is equal to PQ, this means that, and P is greater than Q, this means that P is equal to Q square minus Q minus 1, okay? And since R is not equal to P, there's only one option, which is R square minus R minus 1 is equal to Q. And if we have C like this, S should be like this or like this, and this is contradiction because C is not equal to A or B, so C is simply equal to Q. And for D we can't so D should be Q times something A, for example, okay? So D is equal to QA, let's say. A is not equal to Q squared minus Q minus 1. A squared minus A minus 1 is not Q, and A is not 1 because we already have that. And this implies contradiction, which means that we can't have 4 different numbers which have greatest common divisor more than 1. And with this we are done. It was quite challenging but pretty straightforward. This is a well-known thing that if if P works, then try opposite divisor. This was pretty straightforward, and in this second part you just had to brute force things. This was not like high skill thing to do. It was just brute forcing, and this finishing touch was also like at max 1 point. If you missed this, it was a okay. We are done. It's late. I'll probably go sleep, and goodbye everyone. Peace.